আচ্ছা দেখো, আজকে আমরা আহ, আগের দিন যেটা পড়েছিলে, আহ, আমরা পড়েছিলাম in the last class. There is a concept which is called the breakdown, right? This is called junction breakdown. And what is breakdown? We know there are two type of breakdown. One is called avalanche breakdown and one is called Zener breakdown. One is called, you can say, avalanche breakdown, and another is called Zener breakdown. In the previous class, we discussed up to this that one is the avalanche breakdown and one is the Zener breakdown. And we learned that the avalanche breakdown that will occur, due to the kinetic energy of minor area that becomes so large that they knock out electrons from the covalent bond of the semiconductor material. And in case of this is the happening for the avalanche breakdown, that means due to collisions the electron will be liberated. And in case of Zener breakdown, when you are giving a high reverse voltage, the depletion region that will expand and the potential barrier also increases, that will leading to a very high electric field across the junctions, that will create a very high electric field across the junctions, and the electric field will break some of the covalent bond of the semiconductor atoms, and that will lead to a large number of free minority carriers, which suddenly increase the reverse current. So that means one is due to the collisions and another is happening due to the electric field. And the thing is that, in that particular case, what will happen, that this either this two background, that means you can say either this either of the two, that means avalanche breakdown and Zener breakdown may occur may occur independently. That means it is not sure that in some diode there is avalanche breakdown and in some other diode there is general breakdown. This is not the case. Either of the two that will may occur independently, independently, or you can say both of this may occur simultaneously. May occur, you can say, simultaneously. Generally, diode junctions that break down below 5 volt, we already mentioned that diode junctions, diode junctions that you can say break down, that is below 5 volt, are that will be caused by Zener effect, that will be caused by Zener effect, and junctions, and you can say junctions which experience breakdown above 5 volt, junctions you can say that experience breakdown, you can say above 5 volt, that are, you can say, caused by avalanche effect, that will be caused by avalanche effect. And the thing is that, and generally, Zener breakdown that will occurs in heavily doped junctions, right? Generally, you can say that this breakdown, generally this Zener breakdown that will, you can say, occur for heavily doped. That means if this is a heavily doped, then actually the Zener breakdown that will occur. That means Zener breakdown that will occurs, you can say, in heavily heavily doped junctions, heavily doped junctions, and generally an a heavily doped junction which produce narrow depletions region, which actually produce produce, you can say, narrow depletion region, narrow depletion region. An avalanche breakdown that will occur, you can say, avalanche breakdown that will occur, avalanche breakdown that generally, you can say, occurs in lightly doped junctions, in lightly doped junctions, and of course lightly doped junction which produce, you can say, which produce wide wide depletion, wide depletion layers, wide depletion layers. So, and of course, the Zener diode that have a negative temperature coefficient, while the avalanche diode has a positive temperature coefficient. I already mentioned that positive temperature coefficients. What does it mean? That means when you increase the temperature, that means in case of metal like that. In case of metal, what will happen? When you increase the temperature, the metal, the electrons, the free electrons are vibrating. That means you have to supply more voltage for getting the same current. That means the resistance will increase. That means that will be positive temperature coefficient. So in that case also the same thing. That means Zener diode have a negative temperature coefficient while the avalanche diode have a positive temperature coefficient. So that is, you can say, the part of Zener diode. And you understood the thing in the previous class. We do some, we write some formula, like uh, there is a formula of forward current, I think so. You remember that I wrote this particular formula in the previous class, where I equals to is, this is a reverse saturation current, and this is a exponential, this is E into voltage by eta kBt and minus 1. This is the corresponding formula, where I is the forward current, is, that is nothing but reverse saturation current exponential EV by eta kVt, and that is also, if we put it into formula, then it, it should be written in a different format, right? So you can say that the problem that may come like that, mm, applied voltage, that is V, current is given. So, and there is a thing that we mentions here, that if we put the value, if we put the value, that means, you know, the value of kb, this is Boltzmann constant, is 1.38 into 10 to the power minus 23. I am taking this T as a room temperature 300 K, and you know the electronic charge, you 1.6 into, you can say, 1.6 into 10 to the power minus 19 coulomb. So these are the corresponding constant thing. So here we can say, because since the temperature that is not, this is a room temperature, if the room temperature is given, if the room temperature is given, it should be like that. So the thing is that if we put that, that means is, you can say, exponential E is 1.6 into 10 to the power 3. It should be like that. The formula can also be written like that. This is V by eta Vt, Et eta Vt, where Vt is nothing but If we put that, this is T by 11,600. You don't have to remember that, but the formula can also be written like that. There is a term, this is voltage, that means this is a Vt is nothing but volt equivalent temperature, because in some questions it may be given the value of Vt is given, it is nothing but the volt equivalent of temperature. That means I just put this value of E, I am just putting this value of Kb, then it becomes like that T by 11,600 I can take is a Vt. Vt is nothing but volt equivalent of temperature. And at room temperature, at if we put this value, that means T is equals to 300 and K, then Vt will come out 2.6 millivolt if we put that, right? It's something 25.8, but in if you just, you know, if you just do that, it should be near about 2.6 millivolt. Why I'm written this particular formula? The reason behind that, a questions that may be asked, you just see, it questions may be up there. Say it is given that a diode current that is 0.6 milliampere, when you can say the applied voltage is 400 millivolt, and you can say 20 milliampere, when applied voltage is this and 20 milliampere is the current, when the applied voltage is 500 millivolt, and you have to find the value of eta. Assume You have to assume that Vt is equals to 26 millivolt. It is given. So what we can do, we know the formula. We know the formula that I is equals to, this is Is exponential, this is V by eta Vt minus 1. Approximately you can write, I can just neglect the term 1. So approximately it should be eta Vt. I can write like that. So in that case, diode current, when this is zero point 0.6, applied voltage is this, and when the diode current is this, applied voltage is this. So that means you can say, when the diode current, that means I, equals to zero point 0.6 milliampere, we don't know about Is, you know the voltage, that is 400, and this is a 26 millivolt. All the millivolt and millivolt are there, so I cannot change the unit. So Vt is nothing but 26. You can write like that. And second equations, when the current is 20 milliampere, this is Ix, and this is the exponential. The voltage is 500, and this is eta, and this is also Vt is constant, that means 26. So now if you divide this two, if we divide this two, that means this is exponential e to the power eta 26 by exponential, this is 500 by eta 26, is equals to 20 by 0.6, that means 33.333. And you know, if this is exponential, that means this 400 minus 500, whatever be the thing. So if you do that, it would be, you can say, sorry, this is a 500 and this is a 400. I am making the ratio like that. So 400 minus 500 minus 400, that means 100. That means this is exponential 100 by eta 26, that is equals to 33.33, or you can say eta can be written as 100 by 26. This is log when you 33 one, and that would be nearly 1.097. So that is the procedure by which, if this type of questions are given, you can solve it accordingly. Now there is a questions from the, you can say, there is a questions from the Zener diode. It may be there are some questions from the Zener diode. So the first thing you have to know that uh, we already mentioned that what is the Zener diode applications, right? That means this is also important. But if you see different types of NEET questions and as well as the JE questions, you will find that there are some questions which has been asked from the Zener diode, right? So the basic application I already told you in the previous class that this is nothing but Zener diode shunt regulator. That means Zener diode shunt. Shunt means when this is connected in parallel regulator, or this is called voltage regulations, right? That means output voltage is constant. That means when the Zener diode is placed in a reverse bias parallelly, what will happen across the Zener diode? The output voltage is constant. So voltage regulation is nothing but the measure of a circuit's ability to maintain a constant output voltage even when the input voltage or the load current varies. আগের দিন আমরা বলেছিলাম যে এই যে আমাদের ভোল্টেজ রেগুলেটর তার মানে ইনপুট ভোল্টেজের ফ্ল্যাকচুয়েশন হলে হোয়াট উইল হ্যাপেন আমরা আউটপুট ভোল্টেজটাকে উই অলওয়েজ ট্রাই টু প্লেস ইট ইন এ কনস্ট্যান্ট যেন আউটপুট ভোল্টেজে যেন সবসময় কনস্ট্যান্ট থাকে সেটা আমরা চাই যেটা আমরা ভোল্টেজ স্টেবিলাইজার ইউজ করি বা এখনকার যুগে টিভি ফ্রিজ এইসবের ভেতর ইন্টারনাল স্টেবিলাইজার অলরেডি লাগানো থাকে সেটা অটোমেটিক্যালি ভোল্টেজটাকে রেগুলেট করে সো দিস ইজ ভোল্টেজ রেগুলেশনস হোয়াট ইজ দ্য মেজার দ্যাট মিনস দ্যাট ইজ এ এটা কি measure করে circuit stability, that is the circuit stability, circuit stability to maintain, circuit stability to maintain a constant output voltage. Output voltage is always been constant, আমরা এইভাবেই চাই output voltage constant, you can say output voltage, constant output voltage, even when, even you can say when either you can say input voltage, either input voltage or load current varies, load current you can say varies, তার মানে লোড ইনপুট ভোল্টেজ অর্থাৎ লোড কারেন্ট যদি ভ্যারি করে তা সত্ত্বেও আউটপুট ভোল্টেজ কি থাকবে কনস্ট্যান্ট থাকবে দ্যাট ইজ দ্য ফাংশন অফ জেনার ডায়োড তুমি যদি বলো জেনার ডায়োডের কি কাজ তাহলে জেনার ডায়োডের কাজ হচ্ছে এটা so in that particular case what will happen this is the resistance rs this is you can say this is the Zener diode and you just see Zener diode is connected in reverse bias because this is the positive side and there is a output resistance, this is called the load resistance and output is measured here. Here you can say I am getting the output and this is the load resistance RL and this is the Zener diode and this is the supply voltage, that means this is the input voltage say Vs, that is the input voltage, this is the input voltage. So Zener diode that can be used as a voltage regulator to provide a constant voltage from a source whose voltage may vary appreciably. That means আমরা কি বলছি এই যে জেনার ডায়োডটাকে এমনভাবে আমরা ব্রেকডাউন রিজিয়ন মানে রিভার্স বায়াসে অপারেট করব যে ডায়োড ভোল্টেজ ইন দ্যাট রিজিয়ন হুইচ ইজ অলসো দ্য ভোল্টেজ অ্যাক্রস RL দ্যাট ইজ কল্ড জেনার ভোল্টেজ অ্যান্ড এই জেনার ভোল্টেজটা কনস্ট্যান্ট থাকবে তার মানে কি করতে চাইছি যেহেতু রিভার্স বায়াসে জেনার ভোল্টেজটা জেনার ডায়োডটাকে তুমি কানেক্ট করেছো তাই জেনার ডায়োডের অ্যাক্রসে ভোল্টেজটা সবসময় কনস্ট্যান্ট থাকবে যতক্ষণ ব্রেকডাউন রিজিয়নে থাকবে দ্যাট ইজ দ্য বেসিক ফান্ডামেন্টাল থিং right that means as long as the voltage across the load resistor that is less than the breakdown voltage the Zener diode does not conduct just মনে রাখবে as long as as long as voltage across, voltage you can say across the load resistance, voltage across the load resistance, that is RL, that is you can say less than the breakdown voltage, less than the breakdown voltage, that is VZ. The Zener diode does not conduct. The Zener diode does not does not conduct. That is the main thing. So এটা জাস্ট মনে রাখার জন্য। তার মানে এখানে বুঝতেই পারছো সার্কিট ডায়াগ্রাম যদি থেকে, if I am saying the current is is, that means the current that is flowing through this thing, that means is, and at that point that will be divided into two part, one part across through the Zener and one part across the RL. That means I am saying the current is divided with IL and this is IZ. So that means the total current is is, since it is divided into two part, I can write IZ plus IL. And if I want to find the current is, this is nothing but is, you know, the voltage across the Zener diode, that is a Vz, and Vz is a constant voltage. That means input voltage is Vs minus Vz divided by Rs. This is nothing but the current is. এই দুটো ফর্মুলাই আমাদের মেইনলি ইউজ করা হয়। এবারে আমরা অঙ্ক করতে করতে দেখব যে এখানকার থেকে অঙ্ক বা প্রবলেমস গুলো কিরকম দেয়। সো প্রবলেমটা করার সময় যদি কেউ বুঝতে না পারো, you can ask me. So say for the circuit, for the circuit shown below, find what I have to find, the output voltage that you need to find. The second thing you can say the voltage drop, the voltage drop across RS, and the thing is that the current through the Zener, the current you can say through Zener. So the circuit diagram that is given like that, say this is plus 120 volt, this is 5 kilo ohm, there is a Zener diode like that, this is a Zener diode, and there is a resistance, say RL, that is given 10 kilo ohm. This is the output, and this is given, this is a Zener diode VZ, and value of this given 50 volt, right? That means 50 volt is constant. So now from that particular figure, what you have to find, you have to find the output voltage, you have to find the voltage drop across RS, and you have to find the current through the Zener. So what we can say the current is started from this voltage is, and at that point it will be divided into two part. One part is IL that is passing through this, and one part is IZ that is passing through that, right? So if we want to find the corresponding output voltage, I have to find the corresponding output voltage. So output voltage means this voltage, right? That means when you have to find the output voltage, that means first you have to find the IL, right? If we want to find the IL, if we, then we can find the RL. Also, there is also another thing. You just see that 2 point, that 2 point is similar as 2 point because that are parallel connections, and you know that the voltage across Zener, that is 50 volt, and that is also same across VL, right? Because they are parallel connections. That point and that point, what should be the voltage? The voltage is same as at that point. So what we can say, that output voltage, that is VL or VZ, that is nothing but 50 volt. That is the first thing. And then the voltage drop across RS. You have to find the voltage drop across RS. RS, that means this, you know, this resistance is RS. So you just remember that voltage is 120 volt, and across this is a 50 volt. That means the remaining voltage is nothing but the voltage drop across RS. You just remember, if this voltage is given and this is a resistance, and this voltage is also given, this voltage is 50 volt and this voltage is 120 volt, that means the remaining amount should be the voltage across this resistance. So if we say that the voltage drop across RS, this is nothing but the input voltage, say Vs, and minus Vz or VL, and this is 120 minus 50, that should be equals to 70 volt. And the third, the current through the Zener, the current through the Zener. So now if we want to find the current through the Zener, because what we know, the total current, if this is Is, that means that should be equals to Iz plus IL. So if we want to find the current through Zener, that means you have to know the source current as well as you have to subtract with the load current. This is called load current. This is, you can say, IL. And load current means this current. That means the voltage across these 2 points divided by the resistance. And you know voltage across these 2 points is same as voltage across this 2 point is same across this 2 point. And already we know that it's 50 volts. So that means 50 volt divided by the resistance. Resistance is 10 kilo ohm. So if I am saying I am getting 5 milliampere, and that is the corresponding load current. And what is the source current? If we want to find the current through Is, source current, that means the total voltage across, the voltage drop across Rs, that is 70 volt. So if I want to find, that is nothing but the 70 volt, and the resistance is 5 kilo ohm, because this is a 5 kilo ohm. So 5 kilo ohm, and that will be nothing but 14 milliampere. So if I put this, Is is 14 milliampere minus IL is 5 milliampere, and that will give you 9 milliampere, and 9 milliampere is nothing but the voltage across the voltage that I have current that is passing through the Zener. দেখো বুঝতে পারলে কি বুঝতে পারলে না? আই থিঙ্ক সো বোঝা গেছে। স্নেহা বুঝতে পেরেছো?
হ্যাঁ স্যার।
ওকে, যদি বুঝতে পারো তাহলে আরেক টাইপের অফ কোয়েশ্চেন্স আসতে পারে। আমি এগুলো কিন্তু বলছি দ্যাট ইজ অনলি ফর কম্পিটিটিভ এক্সাম, বিকজ এগুলো জেনারেলি নর্মাল কোয়েশ্চেন্স হিসেবে আসে না। ধরো বললো ফর দ্য জেনার, for the Zener regulator, that is shown in figure, you can say find the maximum, and minimum current flowing through the Zener diode. Current, you can say, flowing through the Zener diode. Flowing through the Zener diode. That means in that particular case, say a variable voltage is given, say range is 85 to 125 volt, and there is, you can say, 5 kilo ohm, that is resistance, and this is the corresponding Zener diode that is connected in the reverse bias, and say this is, you can say, the corresponding, you can say this is a 10 kilo ohm, that is nothing but, you can say, the resistance. So in that particular case, what we can say, that You have to find the maximum and minimum current. So the process is similar. That means what we know, that current, this is the is that is passing through this, and at that moment that would be divided into two part, Iz that would be passing through the Zener, and IL that is passing through the load resistance, that will be passing through the load resistance. So you can say what should be the load current. What we know, the load current is nothing but the output voltage divided by RL. And you know this voltage, that means that 2-point voltage that are similar as the, and of course this Vz is given, Vz is 50 volt, that is given. So the voltage across these 2 point is same as that voltage across these 2 point. That means this is, you can say, Vz by the corresponding, you can say, the resistance, you can say RL, this is 10 kilo ohm. So Vz is 50 by this is 10 kilo ohm, you can say that is 5 milliampere. That is nothing but this. Now the question is, what we know, that Zener current, that means Zener current, that will be maximum, will be maximum, you can say, when input voltage, when input voltage is maximum, because you know this IL is fixed, IL is fixed 5 milliampere. That means if the input voltage is maximum, the current is maximum, input voltage is minimum, that means the current is minimum. So the Zener current, that will be maximum when the input voltage is, you can say, maximum, that is 125 volt. That means if I am find Ix max, this is nothing but Vs max minus output voltage. That means this is output voltage, this is the output voltage, divided by the resistance. That means 125, output voltage is constant, that means voltage across the Zener, and Rs is 5 kilo ohm. This is the Rs 5 kilo ohm, and you will get, that is 15 milliampere. And then what should be the Zener current? Because what we know, Is, that is equals to IL plus Iz. So Iz equals to Is, in that case maximum minus IL. Maximum is 15 milliampere and the load current is 5 milliampere. So the maximum Zener current is 10 milliampere. As well as if we want to find the minimum, that means Is minimum, that means this is voltage is minimum, V out is always been constant, that is similar as the Zener voltage, that means V minimum is given 85. So 85 minus V out, that is 50, divided by Rs, that means 5 kilo ohm, and that will give you 7 milliampere. And hence this is a 7 milliampere, that means similarly Iz, this is Iz, you can say maximum. So if we say Iz minimum, that means Is minimum minus IL is constant, this is a 7 milliampere, this is a 5 milliampere, that will give you 2 milliampere. That is the corresponding answer. Sagnik, বুঝতে পেরেছো?
হ্যাঁ স্যার।
Okay, very good. So this is the thing, যেটা তোমাদের বলা, যে এই রকম টাইপের কোশ্চেন্স তোমার ম্যাক্সিমাম আসতে পারে। আশা করি এইগুলো যদি বুঝে থাকো তাহলে মোটামুটি বাকি যে কোশ্চেন্স আসবে সেগুলো তোমরা ফেস করে অ্যান্সার করতে পারো। দ্যাট ইজ দ্য মেইন থিং। সো তাহলে আমরা দেখলাম দিস ইজ ওয়ান টাইপ অফ থিং যেটা আমরা অলরেডি দেখলাম যে জেনার ডায়োড নিয়ে কাজ করা হয়। এখন প্রশ্ন যেটা হলো যে আদার কি কাজ করে, মানে ডায়োডের আরেকটা মেইন ইম্পর্টেন্স কাজ যদি তুমি বলো তাহলে হোয়াট ইজ ইট, মানে সেটা কি, সেটা যদি দেখি, দ্যাট ইজ কল, ইউ ক্যান সে, রেকটিফায়ার। দ্যাট ইজ কল rectifiers, that is called, you can say, rectifiers. সো রেকটিফায়ার্স মানে কি? সবচেয়ে ভালো এক্সাম্পল যদি রেকটিফায়ারে দেখো তাহলে তোমাদের মোবাইল চার্জার, যেটা তোমাদের হাতের কাছে আছে সেটাই তুমি জানো। হাতের কাছে কি আছে মোবাইল চার্জারে? যে তোমরা দেখো, আমরা মোবাইলের কোনো জিনিস যখন তুমি করো, দ্য ইলেকট্রনিক সার্কিটস কিন্তু এসিতে কাজ করে না, তাই তো? তারা কি করে? ডিসি কারেন্টে কাজ করে, যে কোনো ইলেকট্রনিক সার্কিট। সো তার মানে আমাদের যে বাড়িতে যে পাওয়ার সাপ্লাইটা দেওয়া হয়, সেই পাওয়ার সাপ্লাইতে কি আসে? দ্যাট উইল কাম অ্যাজ এ ফর্ম অফ এসি, অল্টারনেটিং কারেন্ট। এবং অ্যাজ ওয়েল অ্যাজ তুমি যদি দেখো যে কোনো ইলেকট্রনিক সার্কিট, তুমি মোবাইল চার্জার লাগাচ্ছ, তুমি মোবাইল চার্জারে হাত দাও, তোমার কিন্তু শক খাবে না। বাট 220 ভোল্টে যদি হাত দাও তাহলে কিন্তু শক খাবে। তার মানে অফকোর্স মোবাইল চার্জারটা তুমি যখন লাগাচ্ছ তার আউটপুটটা, মোবাইল চার্জারের আউটপুটটা, সেটা নিশ্চয়ই 220 ভোল্ট নয়, কারণ 220 ভোল্ট নিলে কিন্তু শক খাবে। আমি শক খাচ্ছি না হাত দিলেও, আমরা মোবাইল চার্জার লাগিয়ে রেখে দিই, তার মানে ভোল্টেজটা অনেকটাই কমে যাচ্ছে। তাহলে প্রশ্ন হচ্ছে, তাহলে ব্যাপারটা কিরকম হচ্ছে? প্রথম কথা, ইলেকট্রনিক সার্কিট ডিসিতে কাজ করে। দ্বিতীয় কথা, ইলেকট্রনিক সার্কিট 220 ভোল্টে কাজ করতে পারে না, 5 কি 6 ভোল্টে কাজ করে। তার মানে আমাদের ওখানে এমন একটা ডিভাইস তোমার লাগানো আছে, যে ডিভাইসটা দুটো কাজ করছে। দ্য থিং ইজ, দ্য ফার্স্ট কাজ যেটা করছে, দ্যাট ইজ নাথিং বাট, একটা কাজ করছে কি, সে কি করছে, এসি কারেন্টকে ডিসি কারেন্টে কনভার্ট করছে, এবং অ্যাজ ওয়েল অ্যাজ কি করছে, একটা ভোল্টেজকেও কমিয়ে দিচ্ছে। তার মানে আমাদের সার্কিটটা কিরকম আমরা জানি, ইফ দিস ইজ এসি সার্কিট, দিস ইজ এসি সার্কিট, এটা হচ্ছে ধরলাম এসি, ইফ দিস ইজ এ ইনপুট সিগন্যাল, তাহলে আমরা কি করছি, এটাকে একটা আমরা ট্রান্সফর্মার, ট্রান্সফর্মারটা কি, স্টেপ ডাউন, দিস ইজ নাথিং বাট স্টেপ ডাউন, ইউ ক্যান সে ট্রান্সফর্মার, স্টেপ ডাউন ট্রান্সফর্মারে আমি পাঠালাম। স্টেপ ডাউন ট্রান্সফর্মার কি করলো, ভোল্টেজটাকে কমিয়ে দিল, রাইট? ফার্স্টে ভোল্টেজটা 220 ভোল্ট থেকে ধরো 6 ভোল্ট বা 7 ভোল্ট এসিতে কনভার্ট করলো, রাইট? বাট আমার ইলেকট্রনিক সার্কিট ডিসি ছাড়া কাজ করতে পারে না। এখানে আমরা কি করি, উই আর জাস্ট প্লেসিং দ্য রেকটিফায়ার, আই এম জাস্ট প্লেসিং দ্য রেকটিফায়ার, দিস রেকটিফায়ার। এরপরে বিভিন্ন রকম ফিল্টার থাকে, বাট দ্যাট ইজ নট ইনক্লুডেড ইন ইউর সিলেবাস, বাট ফর সেক অফ ইউর নলেজ, দেয়ার আর সাম ফিল্টার্স and there are some voltage regulator, মানে আউটপুট ভোল্টেজ যেন মোটামুটি কনস্ট্যান্ট পাওয়া যায়, যেখানে আমরা জেনার ডায়োড ইউজ করে পড়লাম। এখানে আমাদের ভোল্টেজ রেগুলেটর লাগানো থাকে, এবং তাই জন্য আমরা একটা ডিসি ভোল্টেজ পাই, দ্যাট ইজ এ কনস্ট্যান্ট ডিসি ভোল্টেজ, দ্যাট ইজ ইউ ক্যান সে রেগুলেটেড, ইউ ক্যান সে ডিসি ভোল্টেজ অ্যাজ এন আউটপুট, এটা আউটপুটে পাই। আমাদের আজকে পড়ার বিষয়বস্তু হলো রেকটিফায়ার্স। তাহলে রেকটিফায়ার্স এর কাজ হচ্ছে, এসি যদি ইনপুটে নিই, দ্যাট উইল কনভার্ট ইট ইনটু ডিসি, দ্যাট ইজ দ্য মেইন ফাংশন, যেটা অফকোর্স মোবাইল চার্জারে তোমরা লাগানো থাকে। দ্যাট ইজ দ্য সিম্পল থিং। তার মানে এটা কিন্তু ডায়োডের ওয়ান অফ দ্য মোস্ট ইম্পর্টেন্ট কাজ। তাহলে আমরা দেখলাম যে রেকটিফায়ার, there is a rectifier, that is a, you can say, device which you can say converts the sinusoidal sinusoidal AC voltage, sinusoidal AC, you can say, voltage into either, you can say, positive, or you can say negative, positive or negative pulsating, pulsating, you can say DC. That means PN junction diode, which conducts when forward bias, and practically that will not conduct when reverse bias, can be used for rectifications, that means for conversions of AC into DC। তার মানে এই প্রপার্টিটা কি, প্রপার্টি আমরা পড়েছি যে পিএন জাংশনের ডায়োডের প্রপার্টি পড়েছি, that PN junction diode you can say which which conducts conducts when you are placing that particular thing in forward biased and practically does not conduct, and that will practically does not conduct when it will be placed in reverse biased. It will be placed in reverse bias. That can be used. That can be used for rectification. For you can say rectification. এটা আমরা rectification use করি rectifications মানে কি that mean you can say conversion of AC into DC, conversion of AC into DC. And the rectifier typically needs one, two, or four diodes, right? And rectifiers may be either half wave or full wave, right? That means you can say that rectifier that can be either half wave, half wave, or either it can be full wave. And in full wave, there are also two types. One is called normally that is called center trap by using center tap transformer and by using bridge. That means bridge wave rectifier. So, what is this? We will see it. The first one that is called half wave rectifier. That is also important in your boards also. Half wave rectifier. And that if you understood the thing, that is very easy. That means what is half wave rectifiers? That means you can say this is the AC current, right? This is the corresponding AC current, and say this is the maximum voltage, and this is minus Vs max. So you can say we know this is 0, this is pi, this is 2 pi, this is the AC voltage, input voltage. Now there is some transformer, because transformer is needed, and step down, because this input that is nothing but the alternating current, and this is 220 volt, right? And I have to convert it into some less voltage, so I am just using transformer, but that is not the functions. That means this is nothing but the Vs, right? After that, and I am placing a single diode. I am placing a simple diode, and I am just giving an resistance. I am measuring the output V out. This is the resistance RL. So that is the thing. That is a circuit diagram, right? So you just remember, I am just drawing the diagram like that. So this is the input, and this is output. Now you just see, what do you mean by AC? The meaning of the AC, that means at certain time that particular side is positive and this one is negative, and the next half this is negative and this is positive. That is the function of AC. That means when I am moving this direction, right? When I am moving this directions, that means this is a positive side and this is a negative side. And when I am moving in the opposite directions, that means this is a negative side and this is a positive side. Now I am considering the first case. So that means this side is positive and this side is, you can say, negative. Then what will happen? You just see. When this side is positive, that means this is a PN junction diode. That means this is in forward bias. That means this diode will conduct. That means the current will be flowing through that, and current will be flowing through that, and that will be completing the circuit. That means from positive terminal I am getting the current I, this is moving, we are getting the output voltage, and then this same current will be back to the circuit, So that means I am getting this positive half, right? I am getting this positive half because current will be flowing. Now, say in the next half, I am using different color, then what will happen? If this side is negative and this side is positive, that means that diode is in reverse bias, right? And when this diode is in reverse bias, that means no current, there is no current will be flowing through that. That means I am not getting any voltage, because in case of reverse bias, a little bit reverse saturation current that will be, that you will get, but that is negligible, right? So I am not getting any negative, any current. And in the next half again, what will happen? This side is again, you can say, positive, and this side is again negative. The diode is in forward bias, again I am getting the current, right? So that means, you just remember, in case of half wave, half, why this is called half? That means only half portions of the AC that we are getting. The remaining portions I am not getting. I think you understood the concept. That means only half cycle of the input wave are used. That's why this is called half wave, because in that case only, you know half, only half cycles, of the input wave, half cycles of the input wave that are used, right? And that's why it is, you can say, called a half wave. It is called a half wave rectifier. It is called a half wave rectifier. So that is the main important observations, because in case of half cycle, only half cycles of the input wave that has been used. So that's why this is called half wave rectifier. তাহলে সাগ্নিক বোঝা গেছে না বুঝতে পারলে না?
হ্যাঁ স্যার, বুঝতে পারছি।
ওকে, আকিফ, you understood the thing? Kushi, because that is the one of the important thing that is called half wave rectifier. But what is the problem of that? In that particular case, what we face, that only half portions are valid, right? The remaining half portions that has not been used. So of course, if we calculate the efficiency is very less, because half portions of the AC current that is wasted, right? So in that particular case, because if we analyze this particular thing that is not included in your syllabus, but there are lots of things that you need to analyze from that. What should be the ripple factor? That means how the output is good or output is bad, that can be measured by using some constant that is called a rectifier, whatever be the thing. But I'm not concentrating on that particular thing. The next thing that is the important thing, that is called the full wave rectifier. Because in case of half wave rectifier, the problem that we face, that during this half cycle, during this half while I'm not getting any current, that means there is a wastage, right? So that's why I am concentrating on the full wave, you can say, a rectifier, full wave rectifier. And in case of full wave rectifier, you know, in the half wave, what we get? Only one half cycles of the input are utilized, but in full wave, both half cycles of the input are utilized. So the alternate half cycles that are inverted to give unidirectional load current, right? That means, you can say, in full wave rectifier, you can say, in in full wave rectifiers, rectifiers, both half cycles, both, you can say, half cycles of the input that are utilized, and you can say that alternate half cycles are inverted inverted to, you can say, give unidirectional load current. Unidirectional, you can say, load current. That means current should be flowing in unidirectional. And there is the first one, that full wave rectifier, that is nothing but the center trap, that is called center tap full wave rectifier. Center tap full wave rectifier. And in case of center tap full wave rectifier, we are using two diode, right? We are using two diode. That means you can say the circuit diagram is like that. This is the input AC current. This is the transformer, step down transformer we are using, and I am placing a diode D1 here and the diode D1 D2 here. Say this is the diode D1 and this is the diode D2. And the thing is that the current, this is a center tap. The reason behind that, because you can say, or it will be better if I am right like that. That means in that particular case, the output is measured from there. Say this is the RL, I am getting the V output, right? It should be like that. So in that case, V output I am getting across that. Now how it will work, right? Say this is the input voltage. Say this is the input voltage. And I want to draw the output voltage. So I am designing like that. Say this is the thing. Now you just remember this is a center tap, because from that that transformer, from this center of the transformer I am connecting this, so that's why this is called the center tap, right? So during the first half of the AC current, that means during this positive half, this is a positive sign, this is a negative sign, then you just see the current. This is a positive, this is a negative, this is a negative, this is a positive. That means for the first half of the cycle, this D1 diode that will conduct, because that is in forward bias, but D2 is in reverse bias. That means no current will be flowing through D2. Then what will happen? The current will be flowing like that. Current will be flowing like that. you know the current will not go downward because that is in reverse bias, so current will be flowing like that. I am getting the output, and that will completing the circuit like that. From positive terminal to negative terminal, what I am getting this positive half, because D1 diode is conducting, D2 diode is in reverse bias, so it will not conduct. So in the next half, I am just drawing the circuit again, because since like that, this is the same circuit. There I am measuring the V out. There is another diode, and this is the circuit. I am just for explaining. So in the next half, you just remember what will happen in the say in the say next half. Then what will happen? That portion is negative and this is a positive. That means if this is a diode D1 and this is a diode D2, for diode this is a negative positive. That means D1 diode will not conduct, D2 diode will conduct, right? Because D2 is in forward bias but D1 is in reverse bias. So the current is flowing like that. Current is flowing like that. And what will happen, that you just imagine the current will be flowing in this output. I am getting the current in the same directions, because in the previous case the current is moving in that directions. In the next case also the direction of the current is same, and it will complete the circuit like that. So in the both cases you will get the current in the same directions. That means In the next half again you will get that. That is nothing but the full wave rectifier. I think you understood the case, right? So in that case, when the top of the transformer secondary winding that is positive, D1 is positive with respect to that D2, so only D1 that will conduct, that will be forward bias, so the current will flow from this side, which is directed, directions has been given in the circuit, and I am getting the output, right? And during the second half cycle of the input voltage, you just reverse the polarity. So if you reverse the polarity, then the D1 is reverse bias, but D2 is in forward bias. The current will be flowing like that, and I am getting the output like that. Okay, and that is the, you can say, center tap full wave rectifier. So I think you understood the thing. The only problem of this, you can say, the center tap, because this is a center tap, it is costly, right? So that is the, you can say, the positive thing about the uh, full wave rectifier, because in case of, this is a center tap, so that's why this is nothing but a costliest thing. So that's why there is an alternative way by which you can get the same thing. You are getting the same thing, that is nothing but, you can say, bridge wave rectifier. That means by using this bridge wave rectifier, what you are getting the same output, right? But without avoiding the center trap transformer, because the transformer is tap at the center, and that is costly. So that's why, if I am avoiding this, there is another thing that is called bridge wave rectifier, that is called bridge rectifier. And you already know about the western bridge network, or whatever be the bridge is used in that particular sense also. So you can see that here in the bridge circuit, four diodes are connected in the form of western bridge. That means, you can say, in the bridge in the bridge circuit, you can say, the four diodes that are connected, four diodes are connected in the, you can say, form of a Wheatstone, from of a Wheatstone bridge network. So, and of course, two diagrammatically opposite junction of the bridge that are connected to the secondary of transformer. That means, what is the circuit diagram? The circuit diagram, that means, this is the transformer, this is the input AC current, and this is the connections. I'm just drawing the bridge, right? Here we are using four diodes. Here I am using four diodes, and the diodes are connected as a bridge, and that should be like that. And this is the thing, and you can say the output are connected like that. That means this is RL, and here I am getting the output, right? So you just see, this is nothing but, say, D1, this is D2, this is D3, and this is D4. Just observe carefully. And this is the input AC current. This is the input AC current, and I want to find what should be the output of, this is the input, this is output that I want to get. So at the first half, what will happen? Because that are connected, that means that side is positive, and that side is negative, right? That side is positive and that side is negative. If this will happen, this diode, that means this particular diode that is in forward bias, so the current will be flowing like that, right? The current will not flow through this because the current cannot flow through D2. The reason behind that you will understood, because that is in reverse bias. So the current will be flowing through this directions. I am getting the output. I am getting the output, and the current is flowing like that. The current is flowing, you can say, like that. And at that particular moment, what will happen? If this is connected like that, so that will be moving like that, because I cannot go through the higher potentials, so I am moving along this directions, and I am meeting that, I am completing the circuit. That means only D1 and D3, that two diode are conducting, and I am getting this current, right? And in the next half I am drawing the circuit again, because that is the corresponding circuit. This is the bridge, right? And the voltage is, you can say, like that. So this is the AC current. So in that particular case, and of course I am getting the output from this. This is the, from this I am getting the output. Now what will happen, that in the next case, this particular is negative and this one is a positive. If this is a negative, then if this is a positive, that means the current, it will conduct D2, it will conduct this D2. Then you cannot go backward because that is in reverse bias. So I am moving along this direction, I am getting the output, and then I am moving in that directions. In that particular directions, cannot get to the higher potential, so this particular diode is conducting, that is D4, and the circuit is completing, and I am getting the output. So every time, only two diodes are conducting and the other two diodes are not conducting. That's why we need a fourth diode. But I am getting the full wave rectifier, right? Because the total AC current that will be converted into DC, both half, that means the both half will conduct it. So this is the concept of, you can say, bridge wave rectifier, right? This is the concept of bridge wave rectifier. And there is also something, that means what should be the ripple factor, what should be the, but that is not included in your syllabus. So uh, I understood that you will understood the basic thing of this, all the diode. Because from next class there is a thing that is one of the important thing, that is called the transistors, and that is one of the difficult thing also in your syllabus, that is called specifically bipolar junction. This is specifically called bipolar junction transistor. We will see in the next class, that is called BJT transistor. And of course, this transistor is one of the important thing. That means transistor that is capable of amplifications. That means it will amplify the current. That means it is a current control device. This is the current control device, and it will amplify the current. So that is one of the major purpose of the transistor. Basically, what I am saying, that in our world, the all the classical computers that are built by using the concept of transistors. That is the one of the basic concept. So you can say, if we say, what do you mean by transistor, then the only you can give it, the transistor is an, you can say, the current amplifications device. But the problem that will come from transistor, that is one of the, you can say, important thing. That means you can say that of course the transistor is made up of semiconductor either by using germanium or you can say silicon, but you can say the transistor is nothing but a, you can say the transistor is a current amplification device. So if we just go through the uh, uh, I'm not going details today because that is a totally a huge thing, but there are generally two type of transistors that we have to face. One is called the PNP transistor, that means PN diode, and other is called NPN transistor. That means here you can say the back to back diodes are connected, right? If you connect the back to back diode, then this is nothing but you can say bipolar junction transistor. We will see it in the next class and we will solve some problem because uh, a transistor is itself a uh, huge chapter. That is itself a huge chapter. So I suggest that you should go through the problems that are coming in NEET and all other examinations. Then you will understood